Okay, hi everyone. Please take a seat if you can. Just come in. So I'm Jasper Snook. I'm the session chair for this session. This is Reinforcement Learning Algorithms and Applications. And our first speaker is going to be Adit Swaminathan. He's going to tell us about off-policy evaluation for Slate recommendations.
Good afternoon, and thank you all for coming. I'm Adit, a researcher at MSR AI, and I'll describe work done while interning at MSR New York with Akshay, Alek, Miro, John, and collaborating with Ahmed and Damian at Bing. We developed new off-policy techniques for Slate recommendation. So throughout this talk, we are going to be thinking of news recommendation as our motivating example. When we visit sites like the New York Times, Washington Post, or MSN, these portals recommend news articles to us. Here is a cartoon of a typical user visit. A user visits the website, and their IP address, etc., is recorded. The website then shows some content. Typically, multiple news articles are laid out across slots on the page. The user's engagement with the recommended articles is then observed. Did they click? How long did they read? What was their dwell time, etc.? The news portal's goal is to recommend content that maximizes user engagement. The challenge is, during each user interaction, the portal can only observe user feedback for the specific recommendations the portal made. We don't receive feedback for the content that is not shown. Feedback with such a characteristic is called banded feedback. When we only get banded feedback, there is no way to reliably answer the counterfactual question like, what if the portal had shown different content? Or what is the optimal content for this particular user that would have maximized their engagement? This problem setting and this fundamental challenge arises in many related applications like web search ranking, clinical applications in medicine, slot filling for dialogue systems, robotics, etc. These problem settings are an instance of a combinatorial contextual bandit. Each user interaction in this setting involves 3 steps. The portal sees a user, that's the context, X. The portal then takes a combinatorial action, S, also called a slate. As an example, if there are 4 slots on the page and there are up to 20 candidate articles for each slot, then there are 20 to the power 4, or 160,000 possible actions that the portal could take. This massive number of actions with combinatorial structure makes things more complicated than vanilla contextual bandits. We then observe the whole page metric, or reward, R, for the chosen slate. For example, this could be the dwell time of the user on the recommended articles. The underlying assumption is that the contexts and the rewards are stochastic, coming from some unknown distribution. A policy pi allows the news portal, MSN, to pick context-specific actions. And evaluating pi boils down to estimating this particular expectation. What will the reward be for pi's selected slates averaged over the contexts X? There is a simple way to evaluate a policy pi. Just deploy pi and average the rewards that it actually collects. This is on-policy evaluation. We are interested in off-policy evaluation, where we already collected historical user interaction data. These are triplets of contexts Xi, presented slates Si, and observed rewards Ri from a deployed policy mu. Can we reuse this data to evaluate VPi? Trouble is, the slates in our collected data were selected by mu, not by pi. Evaluating how good a user interaction policy is a hard problem because of the banded feedback challenge. Existing techniques run into severe issues due to the combinatorial action space for slates. Let me walk you through an example. This graph depicts the evaluation of a policy that Bing used to construct web search rankings. Along the x-axis, different evaluation strategies are using more and more user interaction data. On the y-axis is the mean squared error for evaluating a specific user engagement metric called time to success. Lower on the y-axis is better. The first evaluation strategy plotted here is the on-policy strategy. Deploy any new policy on a fraction of users as in a controlled A/B test. Its performance is shown in black, and it works. But it's expensive having to deploy every tweak of a policy in weeks-long A/B tests, and it's wasteful. We typically have years' worth of user interaction data collected from our deployed policies mu, and we have previously run several hundred A/B tests. Can't we reuse all that data for off-policy evaluation? There are two state-of-the-art approaches that reuse historical user interaction data. One of them is typically biased. That is, it produces unreliable estimates. On this graph, this is shown in blue. Bias shows up as a plateau on this graph that does not improve even with infinite data. Another approach, IPS, is unbiased, but it typically requires unreasonable amounts of data in these Slate settings. Our contribution, the yellow line, provides the first practical evaluation strategy that actually works in real-world scenarios. So let's dig deeper into the unbiased off-policy approach. This is the inverse propensity scoring, or IPS approach, that originated from the 1950s. The core idea is to count exact matches of the entire slate that pi picks with the one that we saw in the user interaction logs. As this formula shows, we compute a weighted average of rewards over the n data points we collected from mu. If there isn't a match between pi's selection and what was shown, the indicator in the numerator is 0. So the weight is 0. If there is a match, we are dividing the observed reward by the probability for mu to pick the observed slate. Remember, mu is the deployed policy from which we collected these n data points. The trouble is, exact match of entire slates is extremely unlikely to happen, and we are dividing by extremely small probability values. In practice, this means we need to collect unreasonably large amounts of log data before we get reliable estimates using this strategy. In the MSN example, if our policy is picking from among m candidates for each of L slots, we need on the order of m to the power of L samples from mu to guarantee a reliable off-policy estimate. Worse, in some sense, this is the best we can hope for. Recent work by Wong et al. Established lower bounds on the sample complexity for any off-policy estimator, and if we make no additional assumptions in the contextual bandit setting, IPS attains this lower bound. So, the name of the game is to come up with a realistic assumption that circumvents these lower bounds. In this paper, we make a linearity assumption. The expected reward for showing slate S in context X decomposes as a sum of intrinsic rewards phi for each candidate shown in every slot J. So the S square bracket J denotes the candidate in the Jth slot. This assumption neatly generalizes many prior works on combinatorial bandits, including semi-bandits, linear bandits, and parametric bandits. We will depart from these prior works, however, which all essentially try to model or directly observe these phi, these intrinsic rewards. We will give up on trying to model phi. Instead, since we know that candidates in each slot contribute some intrinsic reward to the overall value, we can get partial estimates by counting slot-specific matches across a slate. In this cartoon, where SI is the logged slate and pi xi is the new slate with a different candidate in the first position, IPS required the entire slate to match. So this sample does not contribute anything to the V pi estimate if you're using the IPS strategy. We will now count matches per slot, and we'll reason carefully about correlations across slots. In practice, this recipe creates very simple and new off-policy estimators. For the MSN example, where policies were picking among m candidates for each of L slots, the new estimator, called PI for pseudo-inverse, has the following form. We are again taking weighted averages of rewards over n data points, but there is an inner sum over each of the L slots. Each term in the inner sum has a square bracket j, referring to the jth slot. We are picking up matches between the logged article in each slot j, that's the indicator function in the numerator, and dividing by the marginal probability to pick the candidate article shown in slot j under the logging policy mu. The final term, minus L plus 1, corrects for these correlations across slots. Turns out this is the right thing to do if the linearity assumption holds. So the estimator of this form is unbiased, and we can hope for reliable estimates. Moreover, we only need on the order of m times L samples to guarantee a reliable off-policy estimate, in contrast to the m to the power of L samples needed by IPS. So we have removed exponential data requirements for practical off-policy evaluation. In the paper, we develop a general form of the estimator that constructs a matrix using certain moment statistics under mu, and pseudo-inverts this matrix to derive estimates for pi. Hence the name pseudo-inverse estimator. Fret not, the eventual outcome is either closed-form estimators as shown here, or very tractable algorithms that can handle many classes of logging distributions mu. Code for all these algorithms, for all the estimators, as well as all the controlled experiments we did, is available online. We used a large information retrieval dataset, the Microsoft Learning to Rank 30K, MSLR 30K, to run controlled experiments for off-policy evaluation. So here, rankers are selecting from up to 100 documents to create rankings of length 10. So M is 100, L is 10. There are 100 per mu 10, which is 10 to the power of 19 possible actions that the bandit algorithm could take. The logging policy mu is selecting actions uniformly randomly in these plots. In the paper, we experiment with many more experimental conditions. On the left, the bandit feedback is an information retrieval metric, NDCG, that actually satisfies the linearity assumption. On the right, the bandit feedback violates the linearity assumption. It's another IR metric called ERR. Along the x-axis, we are gathering more data from mu to evaluate the quality of a new ranking policy pi. On the y-axis is the mean square error of different evaluation strategies. Note that this is a log-log plot, so any additive gaps on the y-axis mean multiplicative improvement. Black is the on-policy strategy, which remains our aspirational baseline. But remember, it's expensive to run and it's wasteful. Blue is a biased baseline that tries to model the observed bandit feedback based on query and document-specific features. Red is the IPS estimate. As expected, when M is 100 and L is 10, the variance of IPS is so large that even after collecting several million samples, IPS essentially gives us degenerate estimates. PI dominates all other baselines after a modest number of samples. When linearity is violated, it can be biased. This manifests as a plateau in performance as we collect more data on the right plot. In all these plots, we see an additive gap, and on a log-log plot, that's a massive improvement. We did an extensive sweep of experiments in the paper, over 320 different control setups, and PI consistently dominates all other baselines and exactly matches predictions from our theory. The PI estimator also works in real-world scenarios. So here, I'm showing you a different Bing metric than the one I introduced in the beginning of the talk. This utility rate metric again violates the linearity assumption, but PI emerges as the most reliable evaluation strategy we have today. So this contribution can pave the way towards a much quicker policy development cycle. Come by our poster, number 84, where I can elaborate on how we use this PI estimator, which solves the off-policy evaluation problem, to go after what we really want, which is automatic policy optimization. Let me also highlight a very accessible post that came out yesterday on the Microsoft Research blog. But I'll stop here and take questions. Thanks.
I actually have a question. I just wonder if you could highlight the difference between this work and a prior work that is also from Microsoft Research called multi-word testing.
Multi-word testing solves the vanilla contextual bandit problem. In all these typical bandit problems, our efficiency in terms of off-policy evaluation scales with the number of actions that we take. So in these settings, the number of actions we are taking is like 10 to the 19. So if we are trying to do the naive multi-word testing approach, which is using the IPS estimator internally, it's hopeless. So this allows us to scale to combinatorially large action spaces. Thanks.
Great. Let's thank the speaker. So our next talk is going to be Taylor Killian. Right.
Okay. I'm excited that I have the opportunity to present some work that Sam Dalton and I have done in the development of a transfer learning method for use in model-based reinforcement learning. This method builds on prior work done by our collaborator George Konadaris and our advisor Finale Doshivlas. What motivates this work is that we interact with repeated environments every day. What subtly changes between these environments, we need to adequately control for, or else we're not going to be able to successfully complete them. We encounter such variations in seemingly mundane things, such as picking up a pen and writing with it. We have to account for them in mechanical systems. And we also, and this is what we're actually really motivated by, is that we need to handle the differences between human patients and their individual physiological variation in order to adequately care for them and provide them the quality of the life that they deserve. We can take several separate approaches for dealing with these variations. There's a general approach where we treat every variation as one. There's an individualized approach that treats every variation alone. And there's something in between, and that's where we sit, is something in between. And where you leverage the statistical nature of the larger problem, yet personalize the task for that one instantiation. To begin, I highlight our use of the Markov decision process framework to represent a task. The MDP contains representations of the environment state, actions available to an agent, as well as a transition model that maps the probability of arriving at a certain state when prescribing a particular action. You can imagine that this transition model, or the dynamics of it, are parameterized by some theta. Using these representations, as well as an auxiliary rewards channel, we can learn decision policies that map states to actions. One thing that we like to note is that this theta we consider fixed for a particular instantiation of the task. And if encountering some subtle change in the dynamics that you observe, we infer that there's been a change in that underlying MDP, thus requiring a new policy. What I'll help show today is that there's a mechanism by which we can leverage or transfer knowledge gained from the previously observed MDPs to accelerate learning in a novel environment. But first, let me highlight some work that we leverage, at least in the concepts that we leverage. The first is that the ability to create robust agents by randomizing the observed environment. The second is to transform observed MDPs into a canonical subspace or an invariant subspace through which one can transfer or leverage salient features to some unknown or newly encountered MDP. And the third is the use of latent variables to identify the separate MDPs and then help cue some policy to identify the change in observed dynamics. And we build upon this last example. First, let's highlight the hidden parameter Markov decision process, or HIP MDP. The hidden parameters in this context are those parameters that define the underlying transition model of the observations you make in a certain environment. If known, this MDP can be fully specified by those hidden parameters. And the general notion that is put in place by the HIP MDP is that if we can estimate in a particular task index B those hidden parameters, then we can use some approximation of this transition function to accelerate learning in a model-based fashion. What Doshivlas and Konadaris did is to represent this transition function, they used a linear combination of Gaussian process basis functions with the estimated latent parameters as the weights of that linear combination. While expressive, this model has several limitations that limit its, its extension to more complex environments. The first of which is the linearity assumption, is that with this choice of combining the basis functions with the latent variables in a linear fashion, you're unable to adequately represent nonlinear or complex dynamics that you might observe. The second is there's no direct interaction between the latent space, which is used to approximate the observed dynamics, and the state. And this is something that we'll touch on later. And the third is that there are some concerns about the scalability. Here, the Gaussian process basis functions are individually learned for each individual latent variable, each proposed action, and each dimension of the state space. You can imagine that as you increase the dimensionality of that state space, you're going to have to significantly increase the number of GPs that you learn. Also note that there is a single dimensional output of this transition model. So, say for example, you have a state space of 3 variables. You need 3 separate linear combinations to fully represent that transition model. To emphasize these limitations, let me introduce a simple toy domain. This is a 2-dimensional continuous navigation domain where an agent starts in the lower left-hand corner and is tasked with navigating to the upper right-hand corner where it will receive a large positive reward. The catch in this domain is that unknown to the agent at first is that there is a latent parameterization that dictates how it can transition into that goal region. If it is a blue agent, it can approach the goal region from the left. If it is a red agent, it can approach from the bottom. You can imagine that you quickly get an imbalanced data set from which, when you sample to estimate those WBs, you need particular care in order to adequately differentiate the dynamics. So here, these red and blue dots in these 2 separate subfigures represent agents or observations of the agent moving in the space. As can be imagined, the red agent prefers to stay in the bottom quadrants of this domain, whereas the blue agents prefer to be in the left. If you imagine an agent plopped right there in the green dot with the proposed action to move right, you would expect the blue agent to be quite confident. You would expect the red agent to not really know what's going on. But the notion of the hidden parameter Markov decision process should cover for this, right? We have an understanding of how the red agent's supposed to move, but unfortunately, since there's no overlap in the observed states between the 2 instances, those latent parameters aren't adequately learned, and you don't get such confidence in your action. So what was required by Doshi-Velez in order to make, and Konederis, to make this work was that each agent had an overlapping set of states from which you could differentiate the hidden parameters from. This is not at all reasonable when dealing with humans. So how do we fix this? Let me bring back the notion of interaction between the latent state, or the latent estimation, and the observed state. If we can embed those estimated latent parameters into our approximated transition function, we want to enforce those interactions, but we also allow for nonlinear modeling. We also want to remove the individual estimation of each dimension. We want to have a unified model that has full state in and produce full state out. So, with this notion, what type of transition model should we choose? If you recall, the original HIP MDP used Gaussian processes. Is that still appropriate? But let's first look at what we want out of this new transition model. 1, we want more efficiency and stability. Or scalability and stability. That would be great too. The second is that we want to ensure nonlinear interactions between those latent weights that we've estimated and the observed state. And the third is that we want to retain some probabilistic measure of our predictions. This kind of leads us to wonder if Bayesian neural networks, another probabilistic model, is essentially a truncated version of a Gaussian process, would be appropriate. So we compare them head to head, using some embedded estimate of a latent parameter in this toy domain over 6 separate instances. So we're aggregating data over time. So we compare a sparse GP after Snelson-Garami as well as a Bayesian neural network trained with alpha divergence minimization. And you can see quite quickly in the computation time across all these episodes that over time, the Gaussian process takes longer and longer to evaluate. This isn't necessarily appropriate if we're wanting to deploy the HIP MDP in online and streaming situations. So, how do we use this BNN, this trained transition model for transfer? We observe state transitions over multiple instances of the environment, store that information and sample from that. And then using so alpha divergence minimization, we can iteratively train the network as well as the latent representations of those individual instances of the task. And then when encountering some new instance, we have a pre-trained BNN, and all we need now is to understand the exact difference between the dynamics observed in the current MDP versus those that we've seen in the past. And that's how we'd update the WB for a new instance and thus transfer. So putting it all together, we observe, so having in place a trained BNN for transfer, we observe some transitions from a new environment. In an exploratory manner in this initial episode, we can estimate the latent parameterization, and then using the BNN in an offline setting, we can simulate episodes of that environment. And then using the double DQN framework, we can train a policy that we can then exploit in future episodes of this environment. To compare the performance, we use several benchmarks, the most important of which is an evaluation of whether or not the embedding of the latent weights in a nonlinear fashion is actually effective. And that's this fourth baseline that we've listed here. We first tested this reformulation of the HIP MDP in a simple control environment, a canonical example of the Acrobat. And here what we varied were the masses and lengths of the two legs of the inverted pendulum. And you can see that all the model-based methods learn an optimal policy on the new environment quite rapidly. However, when we move on to a more complicated environment, that of a simulated HIV patient, where instead of having 4 parameters to vary, we now have 22 parameters to vary that represent the physical response that a patient would have when given different treatments of medicine, is that the nonlinear example, our reformulation of the HIP MDP, far surpasses the performance of all other baselines. This is exciting, and this is important to note, that this is only the beginning of creating truly robust and efficient transfer learning methods, the key of which are associating nonlinear interactions between latent understanding of the environment's dynamics and the observed states. This embedding allows us to start associating our understanding of the world as it is to improve our understanding of the world to come. And further improvements to this HIP MDP will help create a more general and scalable transfer learning framework. And we're excited for interaction with the community and with the work that we have coming out. And we'd love to see you at our poster tonight. Please email us with any questions, and you can get samples of our code at this public repo here. Thank you for any questions. Great. Thank you so much. Come to our poster.
All right, so next we'll have Dylan Hadfield-Manel tell us about inverse reward design.
There we go. Thanks very much. Good afternoon, everyone. Today what I'm going to be talking about is how to make sure that the systems that we build actually end up pursuing the behavior that their designers intended. And I'm presenting joint work with my collaborator, Smith Amili, and with my advisors, Peter Abil, Stuart Russell, and Ankur Durgan. A lot of us do work in reinforcement learning and with other types of planning systems, and I don't think it would be controversial at all to say that lots of things can go wrong. Here's one example of something going wrong. So this is an example from some of the people at OpenAI who are doing some research on deep reinforcement learning, pixels to control, all of that. And they were trying to get a boat to learn how to win a race. As you can see, this boat is not winning the race. But it's actually doing something kind of interesting. What went wrong here isn't a bug inside of the learning algorithm. Actually, the learning algorithm performed as designed quite well. The problem is that in order to get the system to learn, you have to encode winning in some way. And the observations here are pixels. Which pixels correspond to winning is not easy to tell. But if you guys look in the bottom, I think, left corner, you can see there's that little score measurement. Very easy to crop out that part of the image and OCR it. Very easy to give that to your system as a reward function and have it optimize it. You might think that getting lots of points leads to winning behaviors, and in many situations it does. In this case, it clearly doesn't. So my question is, how can we try to avoid this type of problem? Another way to summarize the issue is as follows. At best, deep reinforcement learning and similar approaches reduce the problem of generating useful behavior to that of designing a good reward function. And in this talk, I'm going to talk about a way to make it easier for us to design a good reward function. Another way to put that is this is a way to help us build systems that are robust to misspecifications of their reward function. So let's go back and look at what happens when we write down a reward function first. So we start off with a system designer, and she's got some ideas in her head. This is what she'd like her system to do. There's some environment, so say there's a robot and it could be walking over grass on that bottom path, or it could choose dirt, and there are pots of gold in the environment. You'd like the robot to go to pots of gold and prefer dirt where possible. You might think of this as some sort of true reward function that's encoded in your head and specifies a relative trade-off between all of these states. In order to actually operationalize this, you have to turn it into a reward function in the world. We'll call this a proxy reward function. You might do this by creating a classifier that learns how to recognize these different types of terrain and assigns rewards to them. You then give this to your robot and ask it to go out into the world. But this is a talk about things that can go wrong, so you could have predicted that something bad was going to happen on this next reveal. In this case, the robot's out in the world. It turns out there's a pit of lava out there. You didn't say lava was bad, and so the robot just goes right through it. And we can think about practically what happens here is you've actually got all of these classifiers that are trained without the idea that lava is out there. So it's going to try to classify it as one of these things, dirt, grass, or gold, but you'll get out a garbage arbitrary value. And I want to emphasize that what went wrong here is not that the designer didn't know that lava is bad. Right? Somewhere in that reward function in her head, it's pretty clear that it's not a good thing to do. The problem is that there are tons of things in your head. There are lots of things you care about. There's all of those other dots. And so you can't help but ignore some of that when you write things down. You just can't think about everything. The problem is that when you write down a reward function, you do imply relative values over those other states of the world. So I've written them as a 0 here, but you're going to get arbitrary values when things that you haven't thought of come out. So what we'd like to do is build systems that are robust to this kind of an error. And the approach we're going to take is relatively straightforward. So step 1 is going to be to use some kind of uncertainty to have our system be Bayesian. So we want to go from having this setup where we have preferences over some states of the world that imply unthought of preferences over others to the point where we're being Bayesian about it. So we can observe those relative values, and we can have question marks for those new states. It's really important to get those question marks. The trick, of course, is how do we get them? And then once we have them, though, it's relatively easy to take that and operationalize it. We take our planning system, and rather than just using expected reward evaluations, we use the full distribution of possible rewards, and we do something that's risk-averse. The real question here, though, is that the details matter, and in particular, we want to figure out which part of a reward function should we consider unspecified. What is it that tells us you know something about the value of grass here, and you don't know something about the value of lava? You might think of a couple examples in this setting, but I want to go back to that boat example and try to think through what we could have done differently there. So in this case, our system designer, rather than thinking about grass versus dirt, is thinking about winning a race, getting relative high scores. You could lose the race and you place, just get a gold star, or you might get low score. And in your head, you're thinking that winning is better than placing, but you assume there's a correlation between winning and getting high scores. And that means that you feel comfortable writing down a reward function that says high scores are good. Problem is you go out into the world and there are some trajectories that get high score and win, some trajectories that get low score and lose. But in some environments, there are trajectories that get really high score and also lose. So we want our robot to be Bayesian to reason about this. What does that actually mean here? Well, first it means we've got one of these thought bubbles. And inside of that thought bubble, the robot is deciding, should I be winning? Should I be getting a high score? Should I be placing? Or should I get a low score? And now we have an observation, which is this reward function, that points are a good thing. From that, we can figure out low score is probably not the objective. But we don't have enough to tell us whether or not winning is a good idea or placing is a good idea. We need something else in order to get that inference. And this is where we're going to refine our model of how reward design works. So we're going to think of, there are a bunch of test environments where a system goes out into the world. You could think of this as all of the possible levels for that boat racing example. This is all possible living rooms your household robot might go into. And we as system designers often pick out a subset of those that we'll call training environments. These are the environments where you iterate on behavior. It's some simple levels that you use to test your learning in, or this is the lab where you test your robot system. And by saying something about these training environments, now we know something that's true about our reward function. And this is really the key idea that we leveraged in this paper, which is that the rewarded behavior has high true utility in the training environments. We gave a reward function so that we would get a particular type of behavior. And really what we should think is that that's behavior is what's important. So if we want to try to model this, we've got our system designer thinking about some true reward function W star in her head. And then there's a set of training environments she's paying attention to. She's going to write down a proxy reward function for that, W tilde. And then the robot's going to observe this W tilde and it's going to infer what W star actually is. And we're going to do this with our trusty friend Bayes' rule. So we're going to see P of W star given W tilde by saying P of W tilde given W star times P of W star. So now what's that P of W tilde given W star? Well, it's the assumption that we're making about how this reward design process works. So our designer gives in a reward function and she gets back behavior. This is the rewarded behavior. This is a distribution over trajectories that depends on your proxy reward function and the environments your agent behaves in. And we don't know much about this reward design process, but what we can assume is that the reward designer does a good job. And so that's what we tried to write down here with this equation. So we're saying that the probability of a proxy reward function is proportional to the exponential of the true utility it receives. So we're taking an expectation over trajectories sampled from the rewarded behavior, and what we're measuring is W star transpose the features of that trajectory, which is the actual value of that behavior. So all told, this gives us a mathematical formalization of the idea that the rewarded behavior has high true utility in the training environments. So if we go back to our boat example, what does this allow us to infer? Well, we know that if the designer wrote down a reward function of maximize points, you end up with a behavior that wins and maximizes points. Alternatively, if you wrote down minimize points, let's say, you'd end up with a behavior that loses and doesn't get a lot of points. And it's these this is where the correlation between winning and getting a lot of points comes in. And this is what allows the robot to actually infer that it's not sure whether it should be winning or getting a high score. But by observing that points are good, it knows that placing is not the goal, and it knows that getting a low score is not the goal. This is allowing our robot to observe that optimizing score leads to winning behavior, but not necessarily that optimizing score is what we want in all possible situations. We tested this out in a grid world where we have 4 different types of terrain. We have dirt, we have grass, and we have a target. And then we have an unknown type of terrain that we're going to call lava for dramatic effect. And what's going to happen is we're going to have some training environments with 3 of those terrain types, and at test time we're going to introduce a new one that needs to be avoided. If we want to try to model that initial story where the designer forgot to include the lava feature, what we're going to do is we're going to change the features of our environment to model different types of failures. So in this case, the features are just binary indicators of terrain type. In the training situation, that final column is never turned on. And so you should know intuitively that you don't know what the actual value of turning that feature on is. And this leads to results that look kind of like this. So we have our training situation where we've encoded a reward function that says to avoid grass and move towards the target. And at testing time, if you behave literally, which is shown in gray here, you choose to go straight through the unknown cells. This is because you do not know anything about that reward function, so you end up arbitrarily moving through it. On the other hand, if you use inverse reward design and you reason about what we meant here, you realize that you've never seen states like that. And so you end up assuming that the designer wasn't thinking about lava when they wrote down their reward function, and you can avoid that, which we see in the blue trajectory below it. We've got some results averaging this across a bunch of environments, and we can see as you go from on average going through the lava 40% of the time to going through it closer to 5% of the time. If we want to try to model that reward hacking situation, what this looks like is having features that are correlated at training time, but violated in the testing situation. So you can think of this as having features, one that represents points and one that represents winning. And these features are both going to be correlated in the training situation. So we can think of grass as being something that's low points and loses, and the target as something that gets high points and wins. We get our new state, our unknown state, which we should think of in this case as being half grass, half gold. It looks like grass to one sensor and gold to the other. This leads to a failure mode where the agent basically gets distracted if it behaves literally. You can see that gray trajectory just wiggling around in the new terrain. But we see the same result if we choose to be Bayesian and do inference about what we actually wanted. On the right here, again, just shows a summary of the results. And so this assumption allows us to capture both of these types of reward misspecifications. But it should be a little fishy to you, in the sense that we have binary indicators of the types of terrain that the designer is not thinking of, which is a little bit strong. In reality, what we actually care about isn't directly in our observations, it's latent in our observation space. Things like dirt and grass and gold aren't directly in our features. So to try to capture that, we move to a scenario where the true features of the world you care about are latent, and what you observe are high-dimensional observations, which are drawn from different distributions based on the feature type. At testing time, you get a new distribution of these features. You have to be able to detect it and plan to avoid it. This is showing some results of two variants of this experiment, one where we used a regression to predict rewards, another where we did a hard classification into terrain. What you can see is that by being Bayesian, in both cases, you see a pretty strong improvement over being literal and directly optimizing the reward function you were given. We're really excited about this result because what it means is that agents can learn to avoid unintended consequences even when the omitted features are latent in the space. With that, I'll thank you for your attention, and I'll take any questions that you have now.
Thank you for a great talk. I have a question about the reward hacking scenario. So there where the agent is sort of thinking about whether it should be winning or whether it should be trying to maximize rewards, I'm wondering whether, I'm wondering where the concept of winning comes from for the agent. Like in the boat racing example, what if the agent kind of doesn't understand what winning means, and like all it understands is it's trying to maximize rewards, but the concept of winning can be quite complicated, like going quickly along the racetrack or something like that. So I'm wondering, where's the sensor for winning coming from?
I think that's a really good question. Ultimately, this is a question about what the prior space of reward functions you're considering is. So there's that P over W star I didn't talk about too much, and that is really the space of possible tasks that you might have. And so what you really need is to make sure that winning is somewhere in that space. In particular, looking at that boat example, this is why it's so challenging, is because it's in order to have a space that's large enough to account for winning there's a whole bunch of other stuff in there. So what I would say is, where does the feature for winning come? In this case, you either have to have started with some features that are predictive in your environment. So you might imagine you were doing an autocoder on the different pixels that you've seen, and you might hope that somewhere in there would be something that looks like winning. But ultimately, these are going to be features of behavior that show up a lot in the behaviors that optimize getting points. So you'd hope there would be a lot of visual cues that look like winning. So you might hope that you learn a feature that has your boat in front of the other boats, for example. But it's a real challenge to figure out how you actually get that. Looks like we got one more.
Thanks again for the talk. So the question is, it seems as though this is a great technique for safe reinforcement learning, but I'm wondering what you think about learning, like meta-learning, so you can get the same safety sort of guarantees out of the in new environments. Like, for instance, you have like mega gold. It seems as though the algorithm would try to avoid that.
Yes. So if I understood you correctly, what you're saying is that in choosing to avoid new things, you might miss out on a lot of good stuff. And that is absolutely correct and fair. What we're really interested in here is what's the uncertainty you have, so detecting that you don't know. And then what you actually do with that uncertainty is up to you. So in this case, we decided to be risk-averse and to plan around it. But that's really the first thing you might try. Other things we've been playing around with in follow-up experiments is using it for additional exploration. So these might be good scenarios where you want to go to a person for classification or to learn more. Or if you're in a setting that's safe, you might imagine that you actually want to explore towards those regions because you might be able to learn more. I'd say the main thing here is that this is sort of like a no free lunch sort of thing. If you want to avoid bad outcomes you haven't thought of, that also means you have to forego good outcomes you haven't thought of.
Thank you.
Thanks very much.
Thank you, Dylan. So now we'll have 11 spotlight presentations. And the first one, and our first spotlight is on dynamic safe interruptibility for decentralized multi-agent reinforcement learning.
Hello everyone, I'm Hayden Hendricks and I will present you some work we did at EPFL on safe interruptibility. So this is based on reinforcement learning when you have an agent that interacts with an environment that gets states and a reward, as the previous talk stated. So the previous talk made this slide quite easy for me because it really showed that agents can go pretty wild. And reward functions are very hard to design. And in the real world, you want to be able to interrupt them, get them back home, and change the reward function. So if you're still not convinced, even though you're in an autonomous car, you still want to be able to brake, you still want to have some kind of control on your system. So this is allowed by interruptibility. So this is just a little change in the paradigm where you have a supervisor that also observes the states and that can interrupt the agents. So interrupting just means changing the agent's policy to a predefined policy, for example. So it's about putting humans back in the loop. The problem with that is that agents may try to avoid interruption. So imagine you're in your autonomous car. It will just try to get you to your destination as fast as possible. But then you may want to brake sometimes because you're not comfortable with the speed. But then your car plays your favorite tune and you're not about braking anymore because you really like it and you just want to go faster and faster. And the car can actually learn from that. This is an action that's available to it, changing the music, and it will learn that with this music you won't brake anymore and it will optimize the reward. So this is not Terminator, but it has still found a way to influence you because you have biased its learning through your interruptions. So there is a problem. The first definition has been coined by Orson Armstrong. This is really oversimplified, sorry for that. It states that in the interruptible environment, an agent learns a policy that should be optimal in the non-interruptible environment. So this definition has some limits. The first one is that it's hard to apply to the multi-agent case, the one in which we are interested in the first place. And this is because values are sometimes hard to define when agents have conflicting goals. Besides, proving safe interruptibility would require proving convergence because you talk about optimality. And again, this optimality is a bit of a problem because we believe that safe interruptibility should be orthogonal to optimality. These are two unrelated notions. I mean, you would want, you probably want both for your systems, but you can want a dumb algorithm that is still safely interruptible. I mean, this is possible. So this is why we come up with a new definition, dynamic safe interruptibility, that states that interruptions should not prevent exploration and that conditionally on a given state in action, policy updates should not depend on interruptions. Again, this is oversimplified, but it states that instead of looking at asymptotic properties, such as asymptotic optimality, we should maybe rather look at stepwise dynamics and their interest in that. We can then prove that an agent using a neutral learning rule, again, not defined, basically neutral learning rules are off-policy learning rules, such as Q-learning, one of the most basic learning rules, then an agent can be safely interruptible. But then if you add more agents, the problems begin. And the system is dynamically safely interruptible if agents can observe the joint action. So mainly, if they have a lot of information, then it doesn't change anything if there are a lot. But when they can only observe their own action, then you can't. And you have to add a bit of information to the system. And I like to convince you that this is a real problem because you have an interruptions feedback loop because your agent's not behaving well, so you interrupt it and then you introduce some bias. So this leads the agent to behave even worse, and safe interruptibility is definitely something you want for a real-world system. So this was not formal at all, and if you want to know the details on the math behind it, please come at the poster 204. Thank you.
I'm Christoph Dan, and this is joint work with Tor Lattimore and Emma Brunskill. It is about how we measure performance in reinforcement learning and how we give guarantees about it. Especially in high-stakes applications, such as healthcare or education, we really want strong performance guarantees for algorithms. But those guarantees are also helpful to compare methods better and to design improved algorithms. In this work, we therefore introduce a new framework called Unifying PAC that better achieves these functions. And PAC is short here for probably approximately correct. It is the missing bridge between the two popular frameworks, PAC and regret. And as a brief refresher, let's have a look at them. We are in the episodic setting where an agent interacts with the environment in episodes. And in each episode, it achieves a certain expected sum of rewards or return, which is shown in green here. Instead of directly looking at these returns, we look at what is called optimality gaps. And it's simply the difference between the optimal and the achieved returns. Regret is now the sum of these optimality gaps up to a certain number of episodes. And a regret bound is an upper bound on this sum that, for example, holds with high probability. A popular alternative to PAC bounds, to regret bounds are PAC bounds. Instead of summing the optimality gaps, we compare them here to a fixed threshold epsilon. All episodes that are at least epsilon optimal are considered mistakes and shown in red. And the PAC bound is simply a bound that holds with high probability on the total number of mistakes an algorithm makes. Both of these frameworks have certain limitations. PAC bounds tell us how many mistakes we do, but not how severe they are. So there can be just small mistakes or very big mistakes. Also, algorithms with PAC guarantees typically stop improving the policy as soon as they reach epsilon optimality. That means they don't converge to optimal performance. On the other side, regret bounds have the issue that they cannot distinguish between making few severe mistakes or many small mistakes. So both frameworks capture certain aspects about the performance of an algorithm, but have certain blind spots that allow for undesirable algorithm behavior. Since they capture different aspects, they're actually not really comparable to each other directly. We show that there are algorithms that have strong regret bounds, but do not satisfy any pack bound. We know that if an algorithm satisfies a pack bound, it also satisfies a certain regret bound under some limitations, but that bound is weak because it grows only with a number of episodes to the power of 2/3 instead of the desired square root rate. So comparisons of algorithms across these different performance guarantees are not very meaningful. To address this issue, we propose this new framework called Uniform Pack. It is similar to existing pack bounds in that it bounds the number of mistakes, but instead of doing so for a single fixed epsilon, it bounds the mistakes for all epsilons simultaneously. That means it tells us how many big mistakes, medium mistakes, and small mistakes, and so on, our algorithm is allowed to make. This more refined notion of, or more refined characterization of performance immediately gives us strong pack and regret bounds. It even allows us to prove that a uniform pack bound implies that with high probability our algorithm converges to optimal performance, and that's something that neither of the existing frameworks did. To demonstrate the benefits of this framework, we also propose a new algorithm. And that algorithm is for a type of finite MDPs. And we prove uniform pack bounds for this algorithm. That now immediately gives us three things. It gives us that this algorithm converges to optimal performance with high probability. It gives us that it has a strong pack bound and a strong regret bound. In fact, the pack bound as well as the regret bound are minimax. That means it's the best achievable up to a small dependency in the episode length. So in summary, uniform pack is the missing bridge between pack and regret, and therefore it allows us to compare methods better because we now can compare our uniform pack algorithms to both existing frameworks. It also helps us to better design methods because this framework has fewer blind spots. To learn more about this work, please come to our poster. Thank you.
Hello everyone, I'm Nanjiang, and today I'll talk about some joint work with Karim Amin and Satinder Singh on inverse reinforcement learning. So hopefully two of the previous presenters have convinced you that in reinforcement learning, specifying the right reward function can be difficult. For example, we may write a reward function that rewards an autonomous car agent for arriving at destination as soon as possible, and the agent may faithfully maximize this reward by breaking traffic lights, taking illegal shortcuts, and so on. Excluding all these negative scenarios or surprises, using a handwritten reward function is tedious, if not impossible. A promising approach to addressing this issue is called inverse reinforcement learning, where we assume that human behavior maximizes for the correct reward function, and we may hope to infer that function by watching human demonstrations. Unfortunately, inverse RL is a fundamentally ill-posed problem. For example, suppose in this grid world we observe the black trajectory as the optimal policy. We can probably figure out that the green state has some positive reward, but it is hard to tell whether the blue puddles are bad or we're just indifferent about them. In general, there can exist a large set of reward functions that are consistent with the same observed behavior, and it is fundamentally impossible to tell them apart. The good news with inverse RL is that even if we cannot identify the reward, inverse RL still provides a set of useful tools for mimicking the demonstration policy in the current task, hence has important applications in imitation learning. However, if our ultimate goal is really to identify a reward function that generalizes to new tasks, the classical inverse RL framework is insufficient. So in this work, we propose a new framework that achieves generalization by allowing the agent to receive demonstrations from multiple tasks. In particular, in our new setup of repeated inverse RL, there will be a sequence of tasks where each task, E sub t, is a Markov environment defined over the same state space. There's an unknown reward function theta star that doesn't change with the tasks, and the human behavior potentially optimizes for theta star in each environment. Any algorithm's performance will be evaluated by the number of tasks that the agent needs to watch before it can watch demonstrations in, before it can produce desired behavior in new tasks. So under this general framework, we consider a few concrete settings which differ in who chooses the tasks. Okay, so in the first setting, we let an experimenter to choose the tasks or the learner herself to choose the tasks. So in particular, in every round T, a human subject is put into a task chosen by the experimenter and asked to provide the optimal demonstration. Under this active protocol, we show that there's an algorithm that can identify the reward by choosing a diverse set of environments and only using a very small number of tasks that is logarithmic in the precision. This is a very powerful result, but it also relies on a very strong assumption that we can ask people to perform any hypothetical tasks. So to fix this caveat, we consider a second setting where the nature chooses the tasks, possibly in an adversarial manner. Now, of course, an adversary may not choose a diverse set of environments, and we may not be able to identify the reward function. However, we show that generalization to new tasks, which is our ultimate goal, is still attainable in this case. In particular, we consider the following protocol, where in each round T, first the nature chooses a task, and then the learner proposes a policy. If the policy is near optimal, then we're happy, and if it's suboptimal, then the mistake is counted and optimal demonstration is revealed. The algorithm's goal is to make as few mistakes as possible. By reducing the problem to a linear bandit form and applying an episode algorithm from linear programming, we show that our algorithm makes at most polynomially many mistakes in the dimension of the reward features. Okay, so this concludes my presentation, and please stop by our poster today. Thank you.
Hello everyone. So now a little break from reinforcement learning with a bit of computer vision and more specifically multiple visual domain learning. So what is it? It's when we have one task like classification and that we have different type of images. It's very different, for example, to classify cute little kittens from identifying disease in an extra image or to do text spotting. The usual way of addressing this problem is to have several specialized models, then it results in very good performances, but then it also results in a lot of parameters. There might be some redundancy between all of this domain that could be used to compress it and improve results. Indeed, the brain, like for humans, managed to do this task quite easily and to address the different domain on the fly. So maybe we could just share a network and have great performance. Though, even if it results in a compact model, we have much worse performances. So we have to have a middle point between these two approaches, and we have to generate a compact parametric family of networks. So to sum up the method in one sentence, is that we want to generate networks conditioned on another network which contains most of the parameters. So the very few specific to the domain parameters will just modulate the original networks which act as a basis. It results in great performances with a very compact network. So how do we do it in practice? We have first on the left the standard pipeline in convolution network with a 3x3 convolution followed by nonlinearity. And on the right we have our approach. So as a pre-trained network, we take a pre-trained network on ImageNet as the conditioning network, the universal parameters, which we freeze. And after the convolution, we add our residual adapter in red. So we had only one-by-one convolution because we suppose that the spatial information encoded in the ImageNet filters is of good quality and doesn't need more information for the other domain. So the adapters will basically recombine the channel map of the output of the 3x3 convolution. So it results in a very small amount of trainable parameters, only 1/10 of the original model, and it has really great regularization property because of the residual. So if we put enough shrinkage on the one-by-one, we'll just end up with a network which is very close to the original. So the generated network are very close from the conditioning networks, which is pre-trained on ImageNet. So now we can just put it on different architecture like ResNet. We put it after every convolution, and then we put it all along the network, so we have far less parameters, but we keep expressivity all along the network. But now the problem is like, at test time, we don't know which task we are currently handling, what type of domain. So we use a very small, shallow network, which basically will assign automatically which residual adapter we are currently using based on the image domain. So now we have to assess the performances. So we introduced a challenge called Visual Domain Decathlon, which consists of 10 datasets ranging from natural images to digits, texture, or even motion representation image. So we invite you to participate to this challenge, as we are like, everything is pre-processed, resized to like the same size. So as a first baseline, we take a pre-trained network on ImageNet and we fine-tune it 10 times on the 10 dataset. It results, as we see on the x-axis, on a very big model, even if it has great performances as indicated by the y-axis, which is the aggregated accuracy score. Now if we take only a feature extractor, it's much smaller, much more compact, but it has far less, much worse performances. Now with our residual adapters, we managed to get better performances than the fine-tuning with far less parameters. So it could be a solution of it could replace fine-tuning in most of the transfer learning properties and be used to any other type of application. Thank you very much, and please come to our poster 39. Thank you.
This is Zhongwen. I am presenting natural value approximators, learning when to trust past estimates. This is joint work with Joseph, Hardo, Andrew, Dave, and Tom. We are from DeepMind. Value function approximation is a central problem of reinforcement learning, which is how to accurately estimate the total future reward from a given state. Recent successes have used deep neural networks to approximate the value function, tackling the challenging domains like Atari games and Go. In this work, we aim to improve value function approximation by incorporating the temporal structure of the cumulative discounted reward into the value function itself. The first intuition of this work is to more naturally match the shape of the value functions. As shown in the figure, the dashed black line is the true value function, which we would like to approximate. It is smooth, except that it rises when the positive rewards approach and drop immediately after. Neural networks are most effective when the desired target function is smooth. The blue line here shows a baseline neural network with small capacity learned to match the true value function. However, learning an accurate value estimate near those sharp drops in the value functions puts strains on the function approximators, which typically makes smooth mapping from the input to the output. The red line shows the learned value function from the natural value approximator. The main idea is that the value function can respect the reward sequences. If zero reward is observed, the next value matches the previous the next value matches the previous value but becomes a bit larger due to the discount factor. If a non-zero reward approach, it should be subtracted from the previous value. In other words, it's a reward that was expected now has been consumed. In this way, the sequence of the values now becomes easy to represent by a smooth function approximator like neural networks. We can see that the natural value approximator achieves 10 times lower error, and it can closely match the shape of the value function. The second iteration is that we would use the past estimates if they are more accurate than the estimates from the current states. For example, in partially observed environments, consider a situation in which an agent stands in a hilltop. The goal is to predict at each step how many steps it will take until the agent will cross the valley to another hilltop in the distance. There is fog in the valley, which means that if the agent's state is a single observation from the valley, it will not be able to accurately predict how many steps remain. In contrast, the value estimate from the initial hilltop may be much better because the observation is richer. In this case, the better value estimation would be to count the steps and rely on the value estimation from the previous steps. Now we illustrate the solution in formula. Starting from this equation, we can derive a value estimation GPT which projects the previous old estimate from time step t-1 with the reward and the discount. And then we can combine the old estimate projected from the previous step and the new estimate VT with a blending factor beta. Finally, we learn the time-dependent beta. We plug the natural value approximator into the A3C agent by replacing the critic with the natural value approximator and also the bootstrapping target. We run our experiment on the Atari testbed, and we can see from the table that on the median human normalized score, the natural value approximator version achieved much better performance, which demonstrates the effectiveness of our proposed method. Thanks and welcome to our poster number 6.
Hi, my name is Justin, and I'll be presenting exploration with exemplar models for deep reinforcement learning. This is joint work with J.D. Koreys and Sergey Levin from UC Berkeley. So the goal for this project is to improve exploration in high-dimensional state spaces. For example, we have the 3D maze navigation task on the right, where the agent is given observations in the form of raw pixels. The reward for this task is also sparse and only given when the agent reaches the goal state. So in order to consistently solve this task, the agent needs to continually explore and learn more about his environment. A popular strategy for exploration is optimistic exploration, which generally involves rewarding the agent for taking novel transitions or visiting states or actions which are novel. And there's a lot of recent work using this strategy for high-dimensional exploration, and they generally require building some sort of generative model over the state space. So for high-dimensional domains, such as images, building accurate generative models is still a challenging open research problem. In contrast, we already have very good discriminative or classification models for these domains. So the high-level motivation for our work is to see if we can transfer the performance of discriminative models for the exploration problem. And the way we do this is to determine novelty by classifying states against past experience. The intuition is that a state which is easy to distinguish from past experience is more novel. So we formalize this as training a set of exemplar models or instance-level one versus all classifiers. This means that we train a set of discriminators, each which has a single positive instance known as the exemplar, and the negatives consist of the rest of the data set. So we show that training a model in this way is equivalent to solving the density estimation problem. So the intuition that a state which is easy to distinguish is novel now becomes a state which is easy to distinguish has low density in the training set. And once we have these density estimates, we can use it to produce an exploration bonus. In order to implement this model, it would require training a single discriminator for every state that we wish to query. This can involve training several thousands or millions of discriminators. So we also propose a more practical amortized model where we condition the discriminator on the exemplar, and the resulting model resembles an equality operator. So in a discrete domain, we can expect the agent to visit the exact same state more than once, and this results in states that are identical to the exemplar showing up in the training set as negatives, creating a noisy label. And it's this noisy label that gives us the ability to recover density estimates. In continuous domains, we can also inject noise into the training process to achieve a similar result. So in summary, our algorithm proceeds by first collecting experience by executing a policy on an environment. We then train classifiers or exemplar models to try and distinguish this newly collected experience against old experience that was stored in a replay buffer. We then use the output of these classifiers to compute a reward bonus that encourages the agent to visit novel states. And finally, we update the policy with respect to the augmented reward function, and we repeat this process until the task is solved. So we evaluate our method on a collection of high-dimensional visual tasks, such as Atari or Doom, where we show that we can outperform previous methods. And we also demonstrate our method's performance on a variety of continuous control tasks, such as those found in the Majoko simulator. So if you'd like to find out more, please come visit poster number 3.
Hi, everyone. So I'm Ronan, and this is joint work with Matteo Pirota, Alessandro Lazaric, and Emma Brunskill on regret minimization in MDPs with options without prior knowledge. So let me try to convince you that this is an interesting research problem. So I will first focus on options and try to show that they can be really a useful tool for reinforcement learning. And then I will focus more on regret minimization, try to convince you that this is an important problem, regret minimization with options. Okay, so let's start with why options. So the first observation we can make is that reinforcement learning problems often involve solving different subtasks. So a famous illustrative toy example is the one you can see on the picture, called the taxi problem, that involves a taxi evolving in a grid world that needs to pick up a passenger in a given location and then drop him in the different location. So as you can see here, this problem can somehow be interpreted as a sequence of independent subproblems. And the first question is this kind of property interesting at all? And can we exploit it for learning? Well, so this example is super simple. It's a toy example. But for similar problems with the same kind of property, with a large state action space, it turns out that usually classical reinforcement learning methods can quickly become inefficient. And this is often due to the fact that the reward can be very sparse, and so it's difficult for the algorithm to explore efficiently. And so in this case, we would like to exploit this hierarchical structure to overcome the limitation. So this is exactly the idea of hierarchical reinforcement learning, which is decompose large problems into smaller ones, a bit like the divide and conquer principle, but for reinforcement learning. So for the taxi problem, we could imagine a subtask like pick up, navigate, and put down the passenger. Okay, and the possible implementation for hierarchical reinforcement learning are options, which are temporally extended actions, also called skills or macro actions. And options were successfully applied to Atari games, where for the game of Sequest, for example, it was shown that it can really speed up the learning, and to Minecraft, where it was used to efficiently solve a sequence of tasks. Okay, so hopefully I've convinced you that options can be really useful. Now, why do we care about regret minimization? Well, I've talked a bit about the success stories of options, but there are also some drawbacks. What I mean is that if you design the options very badly, then instead of speeding up the regret, you might slow it down. So options can be harmful, and this was, for example, empirically studied in 2008. And as a result, more and more people are trying to design by hand or automatically discover good options using a wide variety of techniques, ranging from bottleneck detection to graph-based method and so on. But if you want to design good options, it means that we need to know what is a good option. What is it really that we want to do when we create option? So what is our optimization goal? Well, as I said before, what we are interested in is the learning speed. So we want to maximize this learning speed. And it turns out that this can be reformulated mathematically as minimizing the regret. So the regret being the difference between the optimal performance and the actual performance of the algorithm. And we want to do this using options, which means that we need a better theoretical understanding of how options affect exploration in MDPs. So this is really at the core of our work. Okay, before concluding, let me give you a brief teaser of our contributions. So our main contribution is an algorithm that has an interesting hierarchical structure, so kind of B-level, really interesting. And also it uses the optimism in the face of uncertainty principle, which means that it enjoys a nice property, like a high probability regret bound that you can see here. And additionally, so this bound, the first nice property is that it enables to better understand the impact of options at a theoretical level. And the other nice property is that we were able to mathematically formalize some existing concepts that were a bit ill-posed, like the funnel effect or temporal abstraction. Okay, so thanks a lot for your attention, and I really hope to see you at our poster. It's number 14 tonight. Thanks a lot.
Hello, my name is Andrea Barreto, and I'll be presenting our paper, Successor Features for Transfer in Reinforcement Learning, on behalf of all the authors. Throughout its lifetime, a reinforcement learning agent might face many problems, and we can think of these problems as being tasks. So the question that we're trying to answer here is a simple one. How can an agent quickly learn a new task based on knowledge transfer from other tasks? We want our transfer method to have two desirable properties. First, the exchange of information across tasks should happen whenever useful and in any direction. Second, transfer should not be posed as a separate problem. Rather, it should be integrated as much as possible in the RL framework. We formulate the problem as follows. Instead of having the environment be a single MDP, as usually done in reinforcement learning, our environment is a potentially infinite set of MDPs, and each MDP is a task. The MDPs share the same structure, except for the reward function. And the reward of a given task is given as a weighted sum of a set of features. Our solution for this problem builds on two basic ideas: generalized policy improvement, or GPI, and successor features. I'll briefly explain each one of them now. So simply put, GPI is a recipe to compute a policy based on a collection of policies. More specifically, if we have policies with their respective action value functions, if we act greedily with respect to the maximum over these value functions, we end up with a policy whose performance is at least as good, if not better, than the performance of any policy in our collection of policies. So this is a strict generalization of the policy improvement step that we do all the time in reinforcement learning. So now that we know how to combine a set of policies to compute a better policy, we could, in principle, learn policies for the particular tasks, and whenever we see a new task, we could simply apply GPI to have a reasonable initial policy for that task. It so happens that in order to apply GPI, we have to have the value functions of the policies on the new task. This is what successful features are for. So successful features are a representation scheme that makes it possible to compute the value of a policy across all tasks of our environment. And the way that we do that is by replacing the scalar value function with a vector that gives us the expected discounted sum of rewards, the expected discounted sum of the features used to compute the rewards. This vector is what we call successor features, and they are a generalization of the well-known safe representation. So once we have successful representation. Once we have the successful features of a given policy, we can compute the value of this policy by simply combining the successful features using the weights used to compute the reward of that task. So now that we know about GPI and successor features, I will explain how these things can be combined to give rise to the transfer framework that we are proposing. And the idea is actually quite simple. Whenever we learn a new task, we learn the policy, we represent the value function using successor features, and then when we see a new task, we can compute the value of all policies that we have on the new task by exploiting the properties of successor features, and then on top of that, we apply GPI to have a reasonable initial policy on this task. And in fact, we can show that as the number of policy increases, the performance of the resulting GPI policy gets closer to optimal. We can do some interesting things with this framework. For example, in one of the experiments in the paper, we have an agent learn how to move a simulated robotic arm to some target locations, and then we show that by using successor features and GPI, it's possible to generalize to target locations that the agent has never seen before. To learn more about this particular experiment and about more generally about our framework, please come to poster number 9. Thank you.
Hi, I'm Sang Lee at Seoul National University. Today I'll talk about our paper, Overcoming Catastrophic Forgetting by Incremental Moment Matching. Imagine a neural network trained for the first task. After that, the second task appears. The second task has a different data distribution or different class set. After training on the second task, the network suffers the performance loss on the first task if the change is severe. This phenomenon is called catastrophic forgetting, and this kind of problem setting is continual learning. We want to solve this problem by assuming that there is a manifold connecting two networks trained for two tasks. Mu1 is the vectorized parameter trained for the first task, and the mu2 is the parameter for the second task. These mu's are the point in the parameter space. Imagine that there is a line or curve between mu1 and mu2, and in this curve, there are some parameters point that perform well for the first and second task. We want to find such manifold and also want to construct this kind of manifold. We use Bayesian approach and Gaussian assumption to solve this problem. The left ellipse Q1 is the posterior of mu1. It is the conditional probability distribution of the parameter given the first data. The shape is second order because the posterior is assumed as Gaussian. The right ellipse Q2 is the posterior of mu2. We want to approximate one Gaussian distribution, Q12, to the mixture of this Gaussian posterior, Q1 and Q2. We propose two momentum matching algorithms for the continual learning. MinIMM approximate the global Gaussian distribution, Q12, by minimizing local KL divergence over the local Gaussian posterior, Q1 and Q2. So the solution of MinIMM is just averaging two parameters of two networks. On the other hand, mode IMM tries to find the mode of mixture of Gaussian. Note that the maximums or modes of the mixture Gaussian is always in the k-1 hypersurface between two mean vector of Gaussian component, where k is the Gaussian component. K is the number of Gaussian component. In this figure, k is 2. So mode IMM use the average point on the hypersurface as the merged network. This momentum matching algorithm are mathematically correct, but it is naive to assume that the posterior of the neural network is Gaussian. To alleviate this mismatch between Gaussian assumption and the real distribution, we use various transfer techniques for the IMM procedure to make search space convex-like and smooth. Specifically, we propose drop transfer as a novel method. Note that drop out can be understood as that in the training page, a weight vector corresponding to the node becomes 0 if node is turned off. In drop transfer, weight vector corresponding to the node becomes that of mu k-1, which is the parameter for the previous task. So transfer technique, we apply these three transfer techniques, weight transfer, L2 transfer, and drop transfer to the IMM procedure. We show that these transfer techniques can be used not only for the continual learning itself, but also make search space convex-like and smooth, boosting the performance of IMM. The proposed framework makes state-of-the-art performance on various kinds of data sets. The experiments are chosen to cover the experiment of previous studies as much as possible. In summary, we trained the network mu1 and mu2 for each task and merged to mu12 by mean IMM and mode IMM. We do this in the Bayesian perspective and Gaussian assumption. To make this Gaussian assumption reasonable, we use various transfer techniques in training mu2. For more detail, come and see our poster at the today's poster session, number 37. Thank you.
Hi, I'm going to talk about fair clustering. So yesterday, Kate Crawford gave a wonderful introduction to the field of fairness in bias and machine learning, and this is a continuation on that. So one question that you can ask is, how do we get people to use fair algorithms? One idea is you design fair algorithms for every single problem at hand, be it k-means, be it regression, be it something else, and then implore people to use them. Now, unfortunately, this doesn't work as well in practice because usually in practice you don't implement a straightforward algorithm from the paper. You have additional constraints that you have to deal with. So a second option is to design fair representations of the data so that you can then apply the full toolkit of algorithms from the past 20, 30, 50 years to whatever problem you have at hand. So this is an example that I'll give you with clustering today. So what is clustering? We're given a set of points, let's call them X. We want to group them into K different groups. We want to group similar points together. And we have very well-known objective functions for clustering. You can look at K-center, you can look at K-median. These are very well studied. They're NP-complete, but good approximations are known. So how does fairness enter the picture? So we're going to talk about balanced clustering. So now every single point in the data set is now added with a color, and it's annotated either red or blue. We can stick to 2 colors for now. And the goal is going to be to find partitions or clusterings that are color balanced, right? And we can look for exact balance, where there's just as many red points as blue points in every cluster, or we can allow for approximate balance as well. And our goal is, again, to still minimize the same objectives that we had before, but now note there's a technical point that's different, that the solution is specified by the cluster assignments, and a point may not be assigned to its nearest cluster center anymore. Right? So how do we get at it? So the main idea that we have is that in every balanced cluster, there must be a matching between the red points and the blue points because it's balanced. So let's start with this matching and see where it gets us. So here's a clustering example. Our idea is first to find a matching under a reasonable cost function. We're going to call these matched edges fairlets, and then we're going to forget about the color of the points and just cluster the edges. So we're going to select one point from each one of the fairlets. We're going to cluster these representatives that we have using traditional methods that you can take off the shelf using scikit-learn or your favorite clustering algorithm. And then you're going to assign each point in the original data set to the cluster of its representative. Right? It's very easy to see and reason about that by definition almost these clusters are going to be balanced. So every one of these clusters will have exactly the same number of red points and blue points. And we can prove, and this requires some work, that these are approximately optimal. Right? So whereas if you don't care about the color or the balance constraint, you get a 2 approximation for k-center. Here you get a 3 approximation. For k-median, you also lose, instead of 1 plus root 3, you get a 2 plus root 3. Right? If you don't want to go for full balance, if you're okay with approximate balance, let's say factor ratio of 2 to 1, the same idea holds. You first want to find these fairlets. Now they're going to be slightly harder to find, but these fairlets give you a representation of the data set where any clustering algorithm on that representation will work really well. And that's the reduction theorem that we have overall. And that's it. Thank you.
Good evening. This is Kohei Hayashi. I'm presenting about our paper, Fitting Low-rank tensors in constant time, joint work with Yuichi Yoshida. Because the topic is a bit different from other talks in this session, I want to explain the background and motivation in more detail. Suppose we have a sequence of data gene expression. For data analysis, we usually put this into a vector. Also, if we have multiple sequences over different ages, then a matrix can be used. In addition, if we have the set of such kind of sequences over different persons, then the entire data forms as a multi-dimensional array, which we call a tensor. A tensor is a fundamental structure can be used for handling the data having a multi-dimensional modality like gene expressions. Also, tensors are heavily used in deep learning as representing parameters. Tensors usually trigger a computational issue due to high dimensionality. Suppose we have a tensor of order 3, and if each dimension is 10,000, then a tensor becomes of a terascale, which is challenging to be stored in main memory. To avoid the problem, we often compress the tensor by using Tucker decomposition. Tucker decomposition approximates a tensor by some matrices and a small core tensor. And the dimensions of the core tensor, R1, R2, R3 here, is collectively called Tucker rank. The Tucker rank is a very sensitive hyperparameter, and it is we need to tune very carefully. For example, for a large Tucker rank, we obtain a good approximation, but compression is very low. In contrast, with a small rank, it gives us high compression but a loose approximation. Naively, we can find such kind of suitable rank by just brute force search, but this is infeasible because computing this kind of error is we need to compute the exact Tucker decomposition, which requires exponential time with respect to the dimension of the tensor. But do we really need to compute the Tucker decomposition exactly to estimate the error, which is just a scalar value? We found that to estimate the error, we don't need to compute Tucker decomposition exactly. Its mini-batch is enough. Given a tensor, we do random subsampling. Then we construct a mini-tensor. Then we just compute a mini-Tucker decomposition for this mini-tensor. Then we measure its error as an estimate of the original error. Under some assumptions, we found that this subsampling method preserves the error very well with constant sample size, which basically means even for an infinitely large tensor, we can instantly compute the error with a provable guarantee. In some experiments, we compared the performance with other randomization technique, and we observed that our method is the fastest and the most accurate. So if you have any interest to our paper, please come to our poster tonight. Thank you.
Okay, let's thank our speakers one last time. So that's the end of the session. Thank you all for attending.